formula and the 1.56 multiplier originate from the National Electrical Code, specifically Table 310.15b16. This table addresses ampacity adjustment factors for conductors operating at varying ambient temperatures. According to the table, when ambient temperatures surpass 30 degrees Celsius or 86 degrees Fahrenheit, the conductor's ampacity must be multiplied by an adjustment factor. The value of this adjustment factor is 1.56. This adjustment is crucial because a conductor's resistance increases with temperature. This increased resistance reduces the conductor's capacity to carry current safely. The 1.56 multiplier serves to compensate for this reduction in ampacity, ensuring the conductor operates within its safe limits at elevated temperatures. The formula provided represents a simplified adaptation of the complete formula found within the National Electrical Code. The formal equation is expressed as adjusted ampacity equals ampacity at 30 degrees Celsius multiplied by the adjustment factor. For instance, consider an ambient temperature of 40 degrees Celsius. If a conductor has an ampacity of 100 amps at 30 degrees Celsius, the adjusted ampacity is determined as follows: adjusted ampacity equals 100 amps multiplied by 1.56, resulting in 156 amps. In summary, the 1.56 multiplier is implemented to modify the ampacity of a conductor, accounting for the influence of high ambient temperatures on its current carrying capability. The necessity for temperature correction arises from the fundamental properties of electrical conductors. As the temperature of a conductor increases, its resistance to the flow of electrical current also increases. This relationship is governed by the temperature coefficient of resistance for the specific material of the conductor, typically copper or aluminum. Increased resistance leads to a greater dissipation of electrical energy in the form of heat, further exacerbating the temperature rise. If the current flowing through the conductor is not appropriately reduced to compensate for this effect, the conductor may overheat, potentially damaging the insulation, creating a fire hazard, or causing premature failure of the electrical system. Table 310.15b16 in the NEC provides a comprehensive set of adjustment factors for various temperature ranges. These factors are derived from empirical testing and engineering calculations to ensure that conductors are operated within a safe thermal limits. The table specifies adjustment factors for both copper and aluminum conductors, as their temperature coefficients of resistance differ. The selection of the appropriate adjustment factor depends on the specific conductor type, its insulation rating, and the ambient temperature in which it is installed. The application of these adjustment factors is not merely a matter of compliance with the NEC, but a critical element of electrical safety and reliability. Ignoring temperature correction can have severe consequences, leading to equipment failures, property damage, and even personal injury. Therefore, it is imperative that electrical engineers, contractors, and installers thoroughly understand and correctly apply the ampacity adjustment factors specified in the NEC. The NEC provides specific guidelines on how to determine the ambient temperature in various installation scenarios. The ambient temperature is defined as the temperature of the air or earth surrounding the conductor. In some cases, the ambient temperature may be the same as the room temperature, while in other cases, it may be significantly higher due to factors such as direct sunlight, proximity to heat-generating equipment, or inadequate ventilation. The NEC requires that the ambient temperature be determined as close as practical to the conductor and that the highest expected ambient temperature be used for ampacity adjustment calculations. In addition to ambient temperature, the NEC also considers the number of current-carrying conductors in a raceway or cable when determining ampacity. When multiple conductors are installed in close proximity, the heat generated by each conductor can raise the temperature of the surrounding conductors, reducing their ampacity. The NEC provides directing factors to account for this effect, which must be applied in addition to the temperature adjustment factors. The directing factors are specified in Table 310.15b3 of the NEC and vary depending on the number of current-carrying conductors and the type of raceway or cable. The ampacity adjustment and directing factors specified in the NEC are based on the assumption that the conductors are properly installed and maintained. Improper installation, such as loose connections or damaged insulation, can increase the resistance of the conductor and lead to overheating. Similarly, inadequate maintenance, such as failure to clean or tighten connections, can also contribute to overheating. Therefore, it is essential that electrical systems be installed and maintained in accordance with the NEC and other applicable standards. The NEC is a constantly evolving document that is updated every 3 years to reflect changes in technology and industry best practices. It is important for electrical professionals to stay current with the latest edition of the NEC and to understand the rationale behind the code requirement. The NEC is developed by the National Fire Protection Association, a non-profit organization that is dedicated to reducing the risk of fire and other hazards. The NEC development process is open and transparent, with opportunities for public input and participation. The NEC is widely adopted throughout the United States and is considered to be the definitive standard for electrical safety. In addition to the NEC, there are other standards and regulations that may apply to electrical installations, such as state and local building codes. It is important to consult with local authorities to determine the specific requirements that apply to a particular project. The proper application of ampacity adjustment and derating factors is a critical aspect of electrical design and installation. Failure to correctly apply these factors can lead to dangerous overheating, equipment failures, and even fires. Therefore, it is essential that electrical professionals have a thorough understanding of the NEC and other applicable standards, and that they take the time to carefully consider all of the factors that can affect conductor ampacity. The 1.56 adjustment factor discussed previously is specifically applied when dealing with ambient temperatures exceeding 30 degrees Celsius or 86 degrees Fahrenheit as per NEC guidelines. However, it's crucial to acknowledge that this value is a specific instance within a broader spectrum of correction factors detailed in Table 310.15b16. This table presents a range of adjustment factors applicable to various temperature ranges, allowing for precise ampacity adjustments based on the specific operating environment. For instance, if the ambient temperature is significantly higher than 40 degrees Celsius, a different adjustment factor from the table would be necessary to accurately account for the increased thermal stress on the conductor. Similarly, if the temperature is only slightly above 30 degrees Celsius, the adjustment factor would be lower, reflecting the less severe impact on ampacity. The selection of the correct adjustment factor is not arbitrary, but rather a critical decision based on a precise assessment of the ambient temperature conditions. Overestimating the adjustment factor can lead to unnecessary oversizing of conductors, resulting in increased material costs and potentially larger conduit sizes. Conversely, underestimating the adjustment factor can lead to conductor overheating and potential safety hazards. The NEC emphasizes the importance of using accurate temperature measurements to ensure the appropriate adjustment factor is selected. This may involve using calibrated thermometers or other temperature sensing devices to determine the ambient temperature as close as possible to the conductor. In situations where the ambient temperature fluctuates significantly, it may be necessary to use a time-weighted average temperature to determine the appropriate adjustment factor. This approach takes into account the duration of exposure to different temperatures, providing a more accurate representation of the overall thermal stress on the conductor. Furthermore, the NEC provides guidance on how to address situations where the ambient temperature is not constant, such as in environments with cyclical heating and cooling. In these cases, it may be necessary to use more sophisticated calculation methods to determine the appropriate ampacity adjustment. These methods may involve using thermal modeling software or consulting with a qualified electrical engineer. Beyond temperature, the NEC also considers other factors that can influence conductor ampacity, such as the type of insulation, a method of installation, and the presence of other conductors in close proximity. Each of these factors can affect the heat dissipation characteristics of the conductor, and therefore its ability to carry current safely. The NEC provides detailed guidelines on how to account for these factors when determining conductor ampacity. For example, conductors with higher temperature ratings, such as those insulated with thermos in polymers, can typically operate at higher ampacities than conductors with lower temperature ratings, such as those insulated with thermoplastic materials. Similarly, conductors installed in free air can dissipate heat more effectively than conductors installed in enclosed raceways, and therefore can carry higher currents. The NEC also provides directing factors for conductors installed in close proximity to each other. These factors account for the fact that the heat generated by one conductor can raise the temperature of adjacent conductors, reducing their ampacity. The directing factors vary depending on the number of conductors, the spacing between conductors, and the type of raceway or cable. In addition to these specific factors, the NEC also emphasizes the importance of considering the overall system design when determining conductor ampacity. This includes factors such as the voltage drop in the circuit, the short circuit current rating of the equipment, and the coordination of overcurrent protective devices. A well-designed electrical system will take all of these factors into account to ensure that conductors are operated within their safe limits and that the system is protected against overloads and short circuits. The NEC is a complex and comprehensive document that requires careful study and understanding. It is essential for electrical professionals to stay up to date with the latest edition of the NEC and to seek clarification from qualified experts when needed. By following the guidelines and requirements of the NEC, electrical professionals can ensure the safety and reliability of electrical systems.